Okay, so let's go ahead and get started. Here's where we were last time. We were talking about path independence. We had set up this picture, but I didn't have time to do anything with it. So let me remind you what the picture was. We're looking at two curves, C1 and C2. And these curves are related in that they have the same starting point and they have the same ending point. Okay. So said differently, they have the same boundary, and let me write that down. These two curves, so the boundary of C1 is equal to the boundary of C2. That's just a little hypothetical scenario I want to toy with and see what happens. Again, there is a possibility that these curves might be tied in knots and this kind of thing. I claim that for the purposes of what we're trying to show, we can effectively ignore this. There's a mathematical way around this that's beyond what we can do in this course. Punchline, I'm just going to pretend that that's not an issue, and I claim mathematically it's not really an issue. Okay. So, that being said, looking at these curves as I have them drawn here, you can see that between the two of these curves, we can talk about a surface whose boundary is those two curves. So, such as this one that I have shaded in yellow. Now, let me write down that. Let's see here. So, the boundary of this surface S consists of, well, C1 and C2, but now let's think carefully about, which way. Well, there's going to be an orientation vector for this surface, and let's see here. I'm doing this like that, and so thumb, fingers, curling, etc. You see that the boundary of S is C2, and it's oriented the correct way. It's oriented the way that C2 is going. And then C1, but we move sort of backwards along C1, keeping in mind that a boundary is oriented in a certain direction, thinking about swirls. So it's not C1 plus C2, it's C2 minus C1. Oh, whoops. C2 minus C1. And that minus sign is a little bit annoying, and it creates an urge to say, well, why don't we just set it up a little bit differently in the first place? Why don't I just orient C1 to go the opposite direction of the way that I currently have it set up, and then there'll be a plus? And wouldn't that be nice? Why don't we do that? And the reason we don't do that is because then that would put a minus sign up here. If C1 were oriented the opposite direction, then C1 and C2 would no longer have the same boundary. Their boundaries would be negatives of each other. So unavoidably, there's going to be a minus sign in our calculation somewhere. And I think it's nicer to have it like this than the other way. So in other words, said differently, this minus sign is intrinsic to the way the geometry of boundaries works. And it's not a mistake, right? It's not a bad convention. It's reality. Okay, so this is the picture we're going to be looking at. Two curves with the same boundary. Between the two of them, with a minus sign thrown in appropriately, they are the boundary of a surface. And let's see what we can do with that. We're going to come down here now to let's look at this equation. See what's happening in here. The very first thing that I do is I just write down Stokes' theorem as it applies to that surface. So I haven't. There's no tricky curves on this. This is the line integral around the boundary of a surface of a given vector field is the flux of the curl of that vector field through the surface itself. So straight up, Stokes' curl theorem. Well, now wait a second. The boundary of S is C2 minus C1. Saw that on the previous page. So I can rewrite that integral as the difference of those two line integrals, the difference between the integral on C1 and the integral on C2. So two steps there, neither one of which is particularly tricky, but here's the nice punchline. I just want to look at that equation now, the fact that the far left side of this is equal to the far right side. And there's some wonderful little arguments that you can make now about how path independence you can kind of see path independence in the form of this. We have this difference of two line integrals on the right-hand side. Two line integrals over curves that share the same boundary. It screams path independence, right? And curl. It turns out there's a really strong relationship. So I'm going to walk you through the arguments. First, let's entertain the possibility of what happens when the curl of your vector field is 0. If this is our scenario, if our vector field has curl equal to 0, well, then this left integral, we're computing the flux of 0. That means that this integral is 0. That means that this difference is 0. That means that these two integrals separately are the same. In fact, for this vector field, the same algebra would work no matter how we drew those curves. So that means that this vector field is a vector field that's path independent. So, neat punchline. If the curl is 0, the vector field is path independent. And the argument goes the other way as well. Suppose our vector field is path independent. Well, if the vector field is path independent, that means that given curves C1 and C2 that have the same starting and ending points, same boundary, path independence means that these two integrals will always be equal, which means that this difference will always be 0, which means that this flux will always be 0. Now, how could that be? How can you have a flux that's always 0 no matter what surface you pick? Well, only if that integrand field, the curl field, is itself 0. So this argument goes both ways. So said differently, now again, we're ignoring issues about regularity and that kind of thing, differentiability and stuff. Let's not worry about that. But the punchline is, for sufficiently nice fields, the curl is equal to 0 if and only if the vector field is path independent. So, lovely little fact that sort of appends what we already knew. So what we already knew about path independence was that path independence was synonymous with the vector field being a gradient field. So we now have three seemingly, in terms of how they're defined, totally different statements that all talk about exactly the same fields. So vector fields that are gradients of something. Exactly the same fields as vector fields that are path independent, even though these two concepts are defined in very different ways. They're talking about the exact same vector fields. Further equal to vector fields whose curl is 0. Again, defined in a totally different way, totally different description, talking about exactly the same fields. So, lovely set of facts there. I want to write down some words while we're here. This is just semantics, but it's important to know. So a field that has this property is called a gradient field. Of course, because that's what it is, right? Then we have this term path-independent field. By the way, along the way we talked about conservative fields. Conservative fields are vector fields that, well, you can say it in different ways. I like to think of it as a conservative field as a field that's path independent, because that's path independence is what's required for there to be a well-defined notion of the amount of work it takes to get from a starting point to an ending point. That depends only on the endpoints. And that's what is necessary to define potential energy, and therefore a notion of conservation of energy. Different points of view. And now we have this third point of view, which gives us a fourth term, and that is the term irrotational. It comes from there. And think about, why would we call this an irrotational field? Well, curl, think back to the previous section, what does curl look like? Curl is a way of measuring to what extent is there some sort of vorticity. That's the other term that we use. But to whatever extent the vector field represents a fluid that's kind of twisting or spinning or turning around an axis, that axis being the curl vector. So no curl, no rotation, thus irrotation. So the weird thing is that you're going to find all four of these terms are very common. So irrotational, gradient, conservative, and path independent. So heads up, in different contexts you'll see all four of these terms used to refer to, well, of course, all exactly the same vector fields. And so part of your job as someone who understands multivariable calculus is to realize if someone says they have an irrotational vector field, you need to remember that means it's path independent, and that means that it's a gradient, etc. All right, so really neat facts. Okay, that's the end of that section. We had finished most of that last time. I'm going to talk about surface independence now. By the way, when I wrote this section on surface independence, what I did is I actually took the section on path independence and I just mass copy paste the entire thing, and I pretty much went through and everywhere it said path I replaced it with surface, and everywhere it said that I sort of edited minor edits, and then I added some various additional things, of course, but the first cut to a very large extent was a copy paste because surface independence is so similar in its development and other things to path independence. So I want you to notice this as we go through. This is going to look a lot like what we talked about on last lecture in terms at least of the layout on the page. I wouldn't be surprised if there's a typo in here somewhere where I forgot to change something. They're very, very similar in how they break down. So recall that, in fact, let me flip back just for emphasis. So we started off, when we were talking about path independence, with the fundamental theorem of line integrals, relating a line integral to a, plug into the anti-gradient function. And that gave us this idea that the gradient vector, the same value as long as the two curves have the same boundary. Now look what we're going to do very first cut out of the box here. Very analogous thing. Stokes' theorem, relating a flux integral to a line integral. And we're going to make, and I'm going to talk through the details, but I'm going to make an observation about how that means that gradients, curl, see I was thinking about path independence, curl fields have this property that their fluxes are the same as long as the two surfaces have the same boundary. So it's really analogous. Okay, so look for those continuing analogies as we go along in here. So here's our picture. And let's talk first about, let's talk about this first surface up there. And it's got this boundary curve. Oriented that way. Now there's something kind of weird about, if you think about it, what Stokes' curl theorem says about the flux through that surface. The flux through this surface, how would I compute the flux through this surface? Well, I've got to move all the way over that top surface. I'm going to be looking at all the points on that top surface, looking at which direction the normal vectors point. So there's a bunch of calculations that are going to happen on that surface itself. And the curl theorem says, yeah, well, okay, sure, but you don't have to. You can just look at the boundary curve. And even though you're doing a bunch of calculations at points that we're never going to look at on the right-hand side, confining ourselves only to the boundary curve, nevertheless, I'm going to tell you what you're going to get in that flux calculation on this entire surface just by looking on the boundary curve. Again, it seems like a magic trick. It seems impossible that you could determine the results of a calculation involving stuff that's happening on points that you're not even looking at. Of course, the thing that makes it work, the thing that makes the magic trick work is that, well, of course, there's a trick, and the trick is that the vector field is a special field. So that vector field being specifically a curl of something means you're measuring, well, in this case, circulation, and circulations have this accumulating quantity, and so therefore you can add them up and they cancel in the interior. And that's how, of course, we went through that in detail last time. But it's because we have a special field that makes this property work, that you can determine the flux through a surface only by looking at the boundary. Well, a consequence of that is that if you have any other surface, such as S2 here, that has the same boundary, well, how would I compute the flux through S2? Well, I would compute the flux through S2 by doing a line integral around its boundary. It's got the same boundary. Doing the same line integral, I'm going to get the same flux. Okay. And so we get this result that through the first surface and through the second surface, you get the same flux because these two surfaces have, you'll notice, the same boundary. And they're then computed by the same boundary line integral. Okay. So does it look analogous? Did everybody see the connection to path independence? It's very similar to, so in some sense, one dimension up. Instead of a one-dimensional curve with zero-dimensional boundary points, now I'm talking about a two-dimensional surface with a one-dimensional boundary curve. Very analogous. Okay. So again, it's because we have a special vector field, namely a curl field, that we have this property. So I'm going to define this property, say any vector field that has the property that you always get the same value for the flux for any two surfaces as long as those surfaces have the same boundaries. So I need these two surfaces that have the same boundaries as in our example. Very naturally, I'm going to call this property surface independence. And what we saw here, we can restate now as stating that curl fields have this property of surface independence. And that's what I have written here. If it's a curl, then it's surface independent. And I like to write that in this little diagram here, which you might recognize, and we're going to be adding to this diagram throughout this section. So if G is a curl of something, then it is surface independent. Okay, so where did we go from here when we were talking about, in the last section we were doing path independence? What was the next question? The next question was, does the arrow go the other direction? We see every curl is surface independent. Maybe there's other fields that are also surface independent. Or possibly, perhaps, is it that every surface independent field is in fact a curl field? Does it go both ways? And in fact it does. The proof of this second fact isn't very convenient. It's not something that fits in nicely with the course. So I'm just going to state this is a fact. If you have a surface independent vector field, then it's a curl of some other vector field. And again, summarized by having the arrow in this diagram here now go both ways. Okay, so again, with the flipping back and forth, notice a very strong analogy with path independence. Okay, let me show you an example. Let's get our feet wet on this. So we're given a vector field. I'm going to give you an additional piece of information. It's the curl of some other vector field. Now, I don't know what that other vector field is, so I'm not going to tell you what we might call the anti-curl, right, of this vector field. But I'm going to tell you that it is a curl of something. So, this anti-curl exists out there somewhere. Who knows what it is? We have a vector field, and we have a surface S that's part of this particular elliptical paraboloid, but specifically the part that's above the xy plane. So here's our picture. Our surface is that. The elliptical paraboloid, of course, extends infinitely down below here. I just want the part that's above the xy plane. So we have a surface, we have a vector field. Let's compute the flux. So that's the goal of this question. So Yeah. So we're going to compute the flux. Right. Well, there's different ways that you can approach this problem. Now, one thing you can do, right? You are welcome to Chapter 5 this problem. In other words, you can parameterize that surface. It's a graph, right? So you can parameterize it with the graph parameterization. You got the vector field, and you can take a deep breath and plow forward and do all that stuff. I think that would be very inconvenient. Be a lot of trouble. And so I'm going to show you the much easier way to do it. The much easier way is to take advantage of what we know, specifically G being as it is a curl. I know that it's surface independent. And that means that I can take that surface. Oh, by the way, it's oriented upward, stated in the question. And I can trade that surface for any other surface that has the same boundary. Now, the boundary is like that. Again, think about the right-hand rule. Your thumb swirls which way the boundary goes. The boundary goes counterclockwise as seen from above. Can I think of any other surface that has the same boundary? And there are lots of surfaces to choose from. Again, you can make some wacky surface like that. You could make a wacky surface like that has a hole punched in it. Lots of choices. Don't choose those. It's the easy one. Nice, flat surface, upward oriented, to make sure the orientations work right. Nice, simple, convenient, flat surface there in the XY plane. Has the same boundary curve. Let me pause on that and make sure everybody's good. Everybody see how this green surface has the same boundary curve as that blue surface? Different way to think about it. Your blue surface, kind of sitting up here, it's like you can take the blue surface and just kind of shove it down flat into the plane. Just think of it slowly kind of deforming down into the plane. Does everybody see that? Okay. Again, be careful with your orientations. Make sure you orient the green surface correctly. It looks kind of backwards. It's tempting to say, well, wait a minute, but the boundary of if we were to visualize a solid in there, this one's pointing out of the solid, this one's pointing into the solid. It seems weird, but it's really the same in some sense. That, in particular, if you think about this deformation as you sort of deflate that paraboloid, this would sort of deflate down into that. The key point, though, of course, is in terms of right-hand rule, the boundary of the green surface is the same as the boundary of the blue surface. Okay. All right, so that being said, we want to compute flux through the blue surface, and we say, fooey on that, I want to compute the flux through the green surface. It's a lot easier. It's flat. It's got a really easy normal vector. Look at my normal vector here. It's pointing straight up. Highly desirable. So let's compute that one. And specifically, now again here you can rewrite the vector differential with that normal vector explicitly written in there. We know what that normal vector is. That normal vector is 0, 0, 1. The vector field whose flux I'm computing was given. It was that. Conveniently, our normal vector has lots of zeros in it. That means a bunch of stuff goes away. All that stuff goes away. All I'm left with is xy. So what I find then is I have a really simple integral over this bottom surface. And you can approach this. This is basically a double integral. This is a double integral in the xy plane. You can compute it a lot of different ways. My favorite way to compute this would be to observe that this region, S2 in the xy plane, is symmetric over the x-axis, also over the y-axis. The integrand has odd symmetry over either axis as well. And so pick your axis. This integral is 0 by symmetry. Everybody see how that works? So we kept our hands pretty clean in this calculation. The only actual calculation we did here, really, even though it could have gotten pretty ugly, right? We made an argument about surface independence. We had to see what the normal vector was, and I had to do a little bit of multiplying by zeros and ones. Not bad. Right? Everything else is conceptual arguments. So, very cool example. Everybody good? Okay, so what's the next thing that we did? Back when we were talking about path independence, we made an argument that connected path independence to curl. And the way we made that argument is we drew this picture up here, made certain observations about what's the boundary of what, and then we wrote down Stokes' curl theorem. So one dimension up from that is what we're going to do now and talk about divergence. Now let me go back to the picture. We'll look at this picture here. Got these two surfaces. And I'm going to talk about, again, what's the boundary of what, and think about orientations. Let's get this all straightened out. You'll notice that the two surfaces I have, S1 oriented that way, S2 oriented that way, they have the same boundary curve. Okay, so the boundary of S1 is equal to the boundary of S2. So it's two surfaces with the same boundary curve instead of two curves with the same boundary points. Okay. Looking at the picture as I have it drawn here, certain exceptions. I mean, obviously these surfaces could do weird sort of intersection things. But let's just think about the simple case. I claim it's mathematically sufficient. These two surfaces having the same boundary, it's like I've taken two surfaces and glued them together along their boundary, and that suggests that I've enclosed a three-dimensional region. Namely, that these two surfaces between them make the boundary of a solid. And I've already forgotten what I called this solid. I called the solid R. Fine. So boundary of R consists of these two surfaces. Well, now again, let's think about orientations. Is the boundary of R equal to S1 plus S2? Well, no, not real. I mean, that's a problem because, I guess we can see this. The boundary of R, there's a rule that boundaries are oriented away from the solid. S1 is pointing away from the solid. That's nice. S2 is pointing into the solid. So S2 is oriented the wrong way. So the boundary of R is not S1 plus S2. The boundary of R is S1 minus S2. And again, there's that minus sign. So again, it's tempting to say, well, I oriented S2 the wrong way. Why don't I come over here and let's alternatively just choose to orient S2 that way. Then I would have a plus sign here. And I would be happy right up until the point that I noticed that S1 and S2 no longer have the same boundary. If I oriented S2 downward, then the boundary of S1 would be the negative of the boundary of S2. So again, there is a minus sign in this picture, whether we like it or not. It's not a matter of having made a bad or awkward choice. It's a matter of that being intrinsic to the geometry of boundaries. So it's a fundamental fact about geometry, really. So be careful with that boundary there. Again, I made practically the identical point with path independence. Very much the same thing. Okay. All right, so with this picture having been set up, what we're going to do is we're going to write down Gauss's divergence theorem as it applies to that solid. Okay. So here it is, Gauss's divergence theorem as it applies to that solid. copied it down. I mean, I haven't really done anything with it. That's just a straight up immediate application of the divergence theorem. Now, let's further notice, though, that the boundary of R, keep in mind, is S1 minus S2, so I can rewrite the flux through the boundary of R in those two pieces as flux through S1 minus flux through S2. Again, totally analogous to the path independence stuff that we did. Altogether, then, I want to look at this equation that says that this triple integral of divergence is equal to the difference of these two fluxes. And so you can see a huge opportunity for a connection. This, we're looking at two flux integrals through two surfaces with the same boundary curve. This screams surface independence. And that relates to this triple integral. So we see a strong potential for a connection between surface independence and divergence. I'm going to walk you through the argument. You'll notice again that it's extremely analogous to what we've done before. Let's consider what happens when divergence is 0. If divergence is 0, flat, always 0, that means this triple integral is 0. That means that this difference of two flux integrals is 0. If the difference is 0, that means that these two integrals themselves are the same, and that this would apply for any surfaces. And so therefore G is surface independent. And you can turn the argument around backwards. If you have a vector field that's surface independent, then these two integrals are the same. That means that this difference is 0. That means that this triple integral is 0. Now, how could that be? How can you have a triple integral be 0 over whatever solid you could possibly pick? Only if the integrand is 0. And the divergence is 0. So, just extremely analogous to what we did with path independence. Path independent. A vector field is path independent if curl is 0. A vector field is surface independent if divergence is 0. Okay. Everybody good? Right. So let's complete our little diagram down here. We already knew that every curl was surface independent, and I had stated that every surface independent vector field, ignoring regularity conditions, is a curl. And now we have a new fact. Every surface independent field has divergence equal to 0, and if divergence is equal to 0, then it's surface independent. So again, we have three equivalent formulations. The exact same vector fields. Those that are curls, those that are surface independent, and those whose divergence is equal to 0. Three different properties, very differently defined properties, but they talk about the exact same vector fields. Okay. So let me show you the example again. Now this is arguably kind of the exact same example. It's the exact same vector field, exact same surface. Again, the part above the xy plane looks very similar to what we did previously. I'm removing, though, the free hint that I gave originally that, hey, by the way, free information, it's the curl of an unknown vector field. I'm not going to give you that information anymore. So how would we proceed through this example if we did not know from on high that this was a curl? Well, the whole point of knowing that it was a curl was so that we can conclude surface independence. That's the only thing we did with that fact. We now have a new way to conclude surface independence. Given a vector field, take its divergence. See if you get 0. We don't need a magic hint for that, right? I can just compute the divergence straight up. I guess I didn't even show that calculation, but if you take this vector field, compute its divergence, indeed you do get 0. I'll leave that as an exercise for you guys. In fact, look how easy this exercise is. You're taking the x partial of something with no x's in it, the y partial of something with no y's in it, and the z partial of something with no z's in it. So not only is the divergence 0, I'm going to go so far as to say that the divergence is obviously 0. Right? free, easy, 0. So because the divergence is 0, the vector field is surface independent, and everything proceeds as we did previously. Okay, is everybody good? Right. All right. So I'm going to pose that from a computational viewpoint, surface independence is actually better than path independence. And I think this is a really interesting observation. They're analogous, so it's tempting to say, well, aren't they sort of, because of the fact that they're so similar, aren't they equally convenient? And not really. It's a matter of alternatives. It's a matter of, what's your fallback plan? If you don't use path independence, if you could but choose not to, or fail to see that you could do path independence, what's your alternative? Well, if it's path independent, we know it's a gradient. That's what path independence is sort of closely connected to. So any problem where you could have done path independence, you could also find the anti-gradient and use the fundamental thermal line integrals. In other words, we already had just a awesome, powerful tool that we could have used instead of path independence. That's why it was so hard for me to write an example to show you how path independence is computationally useful at all, right? It's because most examples you can just use the fundamental thermal line integrals. We have a great alternative to path independence. What about surface independence? Well, I guess you could rewrite the flux as a line integral using the anti-curl, right? In other words, you could go to Stokes' curl theorem. If you wanted to compute such a flux, you could write it as a line integral using Stokes' curl theorem. But notice what you would have to do if this is what you're given. You would have to figure out how do you find that anti-curl. I don't know if you noticed this, but when we were talking about Stokes' curl theorem, I didn't show you how to find an anti-curl. It's because it's really hard, and we're not going to do it in this course. So from a computational viewpoint, if what you're trying to do is compute a flux integral, usually this is not a very good option unless the anti-curl is given or can be inferred from something about the way the problem is written, something like that. It's not a really good option. Right? So computationally then, surface independence has no good alternative. That makes it more valuable. It's more valuable to us because we're more desperate when we're trying to compute flux integrals. Does that make sense to everybody? All right. Let me make one last sort of geometric observation, sort of a physical observation about how you can visualize surface-independent fields. Remember that a surface-independent field, where did I put it? Here it is. A surface-independent field has divergence equal to 0. We already have tools for visualizing divergence. What does a vector field look like if you know something about its divergence? What does that divergence look like? And the point of view I want to take here is to think about this vector field, this surface-independent vector field, whose divergence we know something about. Let's think about it in terms of, well, what are its sources and sinks? So we're thinking about an incompressible fluid, maybe like how water is flowing along, something like that. And I want to know, how many sources, how many sinks do we have? Well, sources and sinks are what's detected by divergence. So if the divergence is 0, that means that there is no source and there's no sink. That means that what we're talking about is water flowing along, but there's no sort of water hose injecting water into the tank, or there's no sink where the water is draining out, something like that. So in particular, when the divergence is 0, in other words, when you have a surface-independent vector field, what you're talking about, one way you can visualize that is as representing the flow of an incompressible fluid with no sources or sinks. So, for example, water in a fish tank, in a closed fish tank. So, fish tank, fill it up to the top, glass it off at the top. Water can neither get in nor out. The water can still kind of flow around in there, right? But there's no sources, there's no sinks, there's no compression, there's no decompression. That kind of a flow is what surface independent vector fields look like. Okay. All right. Move on to the next section. Lifetime theorems. There's a point of view that says that these lifetime theorems are really just kind of an organization of ideas that we already know. Most of the ideas I'm going to tell you here we already know. I want to start off by organizing some of our ideas in R2. We've already talked about what happens when you look at the boundary of a curve. Naturally connects to the gradient operator, and you get the fundamental theorem of line integrals. Then we talked about an analogous argument where you take a boundary of a two-dimensional region, talk about how boundaries accumulate, blah, blah, various circulation, yada, yada. And we motivated a new operator called Green's operator. And that gives rise to Green's theorem. Okay. Et cetera, et cetera. We have fundamental theorem of line integrals in R3. We have Stokes' curl theorem in R3. We have Gauss's divergence theorem in R3. So notice that these diagrams, and we've talked about this before, but this is the first time I'm kind of bringing them all together on the same page. These diagrams show the analogies between these theorems. Right? Fundamental theorem of line integrals relates to the gradient vector in the same way that Stokes' curl theorem relates to the curl operator. In the same way that Gauss's divergence theorem relates to the divergence operator. The divergence theorem talks about regions and their boundary surfaces. Stokes' curl theorem talks about surfaces and their boundary curves, etc., etc. So there's a lot of analogies that you can see between these theorems on this diagram. I love these diagrams. I think it's a really useful tool for making sense out of these things, just because of how much it shows the analogies. So, for example, if you want to develop a better intuition for, what's this curl thing? What is curl? Well, curl is playing the role in the Stokes' theorem development that divergence played here. To whatever extent you feel like you have a good intuition for what divergence looks like, think about how that developed in here, and then look for analogous connections here. Right, so it's going to turn out that there are other connections on here. So in particular, gradient and curl relate to each other in a strong way. We've actually already seen this. A vector field, which is a gradient of some function. Well, let's see, we talked about that last time. A vector field is a gradient. That means it's path independent. And if it's path independent, then the curl is equal to 0. And so there's that connection there. Well, we just saw moments ago an analogous connection between curl and divergence. If a vector field is a curl of another vector field, it's surface independent. And if it's surface independent, its divergence is equal to 0. So not only are there connections between these operators, so there are analogies between the operators in the form of these boundary theorems, but there are connections between these theorems that we've seen already with path independence and surface independence. And even more than that, there are analogies between those connections. In other words, these connect in exactly the same way that these connect. So a full discussion of all of these is, again, well beyond what we can do in this course. But I do want to mention, just so you know, that there's a huge theorem that relates these connections and these analogies between these connections. And it's the de Rham cohomology theorem. It's very high-level stuff. It's, again, way beyond what we can do in this course. But that's the reason why these connections are there and that these analogies between these connections are there. It's not coincidence It's because there is, in fact, a single statement that's being made about all of these. And these are, what we're seeing here are the tips of this big iceberg down here. So just, in case you're curious. Okay. So I have a little metaphor that I like to talk about these various connections. It's what I like to call the life cycle of an integrand. It's a silly metaphor, so bear with me on this, all right? But I think it's useful. And there are resulting lifetime theorems that we're going to talk about. So let me develop what the metaphor is. Here's our row of integrands, our dimensions 0, 1, 2, 3. So we're looking on our diagram here. If you have a function, if you apply appropriate to where you are in the diagram the gradient operator, then you get a vector field. I'm going to call this the passage of 1 unit of time. Again, it's part of my little metaphor. As time, when you apply the operator, you're letting time pass by 1 unit. All right. So that vector field that you got, you could apply the appropriate operator. Now again, you're at a different stage on the diagram. You're in column 1, and so curl is the appropriate operator to apply at this point. So this then is the passage of a second unit of time. All right. So in this case, for the function that we're talking about here, that particular function, you have 0 that ends up being the curl of that gradient field, and I'm going to call that death. That's a silly metaphor. Okay, and the reason I call it death is because, well, it's 0. Right? It's nothingness. And furthermore, guess what happens when you take the divergence of 0? Well, you get 0. In some sense, once you've gotten to 0, it stays 0. Again, kind of like death. All right, it's a silly metaphor, but I think it's kind of funny. Okay, so along those lines, if you have a something, if it's not 0, if it's alive, right? And if time passes, and if it's still not 0, still alive, then I'm going to say it survived to that point. So what we have here is something that survived to there, and then it died there. Okay, so this particular integrand, again, my little silly metaphor, I'm going to say it had a lifetime of 2. Everybody see what I'm talking about? Again, silly. Okay. So the algebra, specifically, you take this function here. When you take the gradient, you get that vector field. It's non-zero, so it survived to there. You take the curl, that is 0, and so it kind of dies there. Okay, let's see another example just to extend the metaphor. Okay, so here's a vector field. Now I'm starting in column 1 this time, just to show you what it looks like when you're starting in column 1. The appropriate operator is curl. If you compute the curl, well, you get that. That's just algebra. Let you guys fill in the blanks. And then if you take from where you now are, again, the appropriate operator, in this case is divergence. If you take the divergence, well, then you get 0. And so again, death. All right, so now, question. It's tempting to say that this had a lifetime of 2. It was alive here, it died here. But isn't it possible that this might have conceivably come from over there? In fact, maybe it survived into column 1 and therefore had a lifetime of 3. Well, that's actually not possible. And we've already seen a theorem that tells us why this is not possible. If this vector field survived from column 0. If this vector field were a gradient, its curl would be 0, but it wasn't. See, the curl was not 0. So because the curl is not 0, it can't be the gradient of anything. And that means that it didn't survive from previously. This is the sort of the first instance that this little particular integrand shows up. And so born there, dies there, lifetime of 2. Okay, everybody see what we're talking about? Again, the silly metaphor. So why do I use this silly metaphor? Well, it's because of the following very simple statement that I can make. There's one little exception. I'll talk about that later, but every integrand has a lifetime of 2. That's great. And there's so many statements, there's so many facts about, divergence and curl and gradient and how they connect. And this, what if you take the divergence of the curl of the way is that the theorem? They're all summarized by this one fact: everything has a lifetime of 2. Okay. So there's a large collection of theorems here, all of which are sort of wrapped up in that one statement. Okay, so for example, let's look at this first one here. If a vector field on R2 is a gradient, then Green's operator gives you 0. Okay, let's go back to our diagram. R2. If you have a vector field, and if it is a gradient of some function, Green's operator has to give you 0. Said differently, look, if it was born here, it has to die here because the lifetime was 2. Okay. The next theorem here. Well, let me skip down to number 4 here. If Green's operator is 0, then it is the gradient of some function. If you have a vector field, and if Green's operator gives you 0, then that vector field must be the gradient of some function. Well, again, it sort of has to be, because if it dies here, and it had to have a lifetime of 2, it had to be born there. So, again, now you can walk through all 8 of these, or however many theorems we have here. How many is it? Yeah, 8. You can walk through all 8 of these, and basically what all of them say is, again, everything has a lifetime of 2. So I think now I encourage you to look through the details of all of these, but as you're working problems, it's just very convenient to have them all in your mind in this same single simple form of the lifetime. Everything has a lifetime of 2. Okay, let me pause for a second for questions. Nobody. Okay. A couple of quick observations I do want to make. Again, I don't want to worry about regularity conditions and stuff like that. I'm going to assume everything's as differentiable as you need to be. Furthermore, and this is a big one, everything's got to be defined everywhere. You can't have a vector field that's undefined, let's say, at a single point. We've seen some of these already in this course. We talked about gravitational fields defined by a point mass. Well, okay, but that gravitational field defined by a point mass is not defined at the origin, so that's a problem. None of that's allowed for these theorems to be true, for this metaphor to work. It changes things dramatically if the vector field fails to be defined, even at a single point. There's a homework exercise y'all are going to walk through where I'm going to give you an innocent little vector field, seemingly not that bad. It's defined and continuous, etc., almost everywhere except for one little point where it fails to be defined. And you're going to see that train wreck of failure that happens with the lifetime theorems. So that's an important condition there. Okay, there is one exception. You'll notice this conspicuously absent from the theorems that got stated, but constant functions are an exception. It's a sad little exception. But suppose I have a function here, and it's just constant. Well, the gradient is 0. So it didn't get to live its full lifetime of 2. It died too soon. It's the sad story, right? But this is the one exception to these rules: is constant functions in column 0, gradient is 0. Okay. All right. Okay. So, by the way, here's our diagrams again. And by the way, these are the full versions of the diagram. You might want to make a note of the page number. I'm going to encourage you, as we go through the rest of this, well, we have 20 minutes left today. I'll probably say a few more words about Chapter 6 on tomorrow, because I don't think we're going to quite finish everything I want to tell y'all. But for the rest of today and for part of tomorrow, and then for lots of exercises that y'all are going to be doing, I want to very strongly encourage you to make regular use of these diagrams. So again, they're on page 453 of this version of the book. Okay. So now we already knew this was our sort of setup. At the very start of the chapter, we had set up this sort of framework. Then we developed these boundary theorems in R2. And now here's our lifetime theorems. And our lifetime theorems, they tack on very nicely onto the diagram. Let me just explain the notation I'm using here. The solid arrow represents a hypothesis. That's the, if such and such. And then the dotted arrow represents the corresponding conclusion. So this first line that I have here says, if you have a vector field capital F that is in fact a gradient of a little function little f, if the vector field is a gradient, then your conclusion is that Green's operator on that vector field is 0. Right? So analogously then, this says, if you have a vector field where Green's operator gives you 0, then that vector field is a gradient of something. Does everybody see the notation? How I'm representing these two facts. Okay. All right. So likewise in R3, here's our finally completed diagram for R3. And so you see again we have our setup framework that we set up at the beginning of the chapter. We have our 3 boundary theorems, and then we have our lifetime theorems down here. So again, there's 4 of them. So for example, this one says, if a vector field has curl equal to 0, then that vector field is a gradient of some function. Okay. All right. Now, I'm going to make a suggestion for all. This is going to sound ridiculous, but this is actually a perfectly reasonable suggestion, and that is that I want you to memorize every bit of both of these diagrams, and so that you can reproduce the diagrams for yourself on a clean sheet of paper with no reference to anything else. And let me point out how this is not as much as it sounds like. If you were to do that now, character by character, that would be brutally difficult. But don't do that, right? What you want to do is make sure to understand the patterns. These diagrams are chock full of patterns. Here's all you really need to memorize. And that is, which order do these operators go? Everything else you can kind of sort of either you have unavoidably already memorized, or you can kind of just infer from the rest of the diagram. So, for example, what's the relationship between these various kinds of domains? Well, it's boundary. What else have we been doing this entire chapter, right? So, of course, we're talking about boundary operators here. Right? What kinds of evaluations are we talking about? Well, again, we've done a lot of stuff with these in a one-dimensional sense. If you have a vector field and a curve, well, vector line integral. That's what we've done a bazillion things with. Likewise, flux integrals here, triple integrals here, function evaluation there. Now, what about these three theorems? Well, they all say the same thing in their different contexts. Right? So they all say, let me clean this up a little bit. They all say if you have an integrand and if you do what this top part of the diagram tells you to do, and if you have a domain and if you do the boundary operator, then that evaluation, which is that, equals that evaluation, which is that. So the diagram tells you what the theorem is. Right? And then likewise on all these other, let's infer from the diagram what Gauss's divergence theorem says. Well, if I have a vector field, and if I, according to the diagram, I'm supposed to take the divergence of it, and if I have a solid three-dimensional region, and according to the diagram, I'm supposed to take the boundary of that, then this evaluation, namely that, so boundary flux of the vector field through that surface, is equal to this evaluation, namely that, namely a triple integral of the divergence through the original solid. So there's not that much to memorize, really. What there is to do here is to make sure that you understand what the pattern, understand what the diagram is saying. Yes, you do have to memorize the one little, what's the order that you put these three operators. In fact, even that you could argue there's not that much to memorize because there's a Lego kind of thing. I mean, this one's got to fit into that one, right? So, for example, if you put gradient here, you can't put divergence there because divergence would mean that you have to put curl there, but divergence spits out a function. Curl takes in a vector field. It doesn't fit. Right? So there's only so many ways that you could possibly put those down, so it's just really not that much to memorize. Okay, so does everybody see the goal now? Does everybody see how this is a very tractable goal? So I think it'd be a great exercise. Oh, by the way, the lifetime theorems, again, all analogous. Again, they all look pretty much the same. They summarize so nicely with this lifetime of 2. I think it'd be a great exercise to look at this, think about it, think about the patterns, try to persuade yourself that you understand what's going on here. Put all your books away, take out a clean sheet of paper, and reproduce the whole thing. And I'll bet you can do it. Okay, yeah, you had a question?
What does the curly line mean?
The curly line? Oh, I'm just saying if you were to take this specific function and do that to it. So when we draw a straight line, that's typically representing, I consider all possible functions to which I might apply the gradient operator, and every one is going to give me some vector field. But when you're talking about a specific single one, I just want to distinguish that. But both of these are saying do the gradient operator. Yeah. Okay. So give that a try. And then likewise, for the R2 diagram, same deal. I'll bet you can do it. Just make sure to understand what the operators are at the various points. Make sure to understand how the boundary theorems are analogous, how they fit in with what they sort of have to, given the choices that we've made higher up in the diagram. There's not that much going on there. Okay. Right. Right, so example. Let's look at this example. We've got a vector field given. And we have no information as to whether this is a gradient or not a gradient of something. And I'm going to show you how to decide. Now, as of the moment, before, when we were talking about the fundamental thermal rules, the way we decided whether there was an anti-gradient is by trying to find the anti-gradient. Right? We started taking anti-partials for 3 different components. And then we started playing this game of can I make this fit into that, and can I make it all sort of fit together. And there's a certain amount of work there. Well, we have another tool now. We have this lifetime theorem. If I want to know, in R3, given a vector field, if I want to know, is it a gradient of something? The diagram tells you how to decide. The diagram tells you, oh, well, we know the lifetime is 2, so if that were the case, the curl would have to be 0, because that would give it a lifetime of 2. Right, so if you want to decide if a three-dimensional vector field has an anti-gradient, take the curl. See if you get 0 or not. Okay, so going back to this vector field, we have these 3 components. Oh, that's not as legible on the board. Let me do that in yellow. We have these 3 components. The way we take curl, don't forget, is we draw this little, there's a little symbolic determinant, partial with respect to x, partial with respect to y, partial with respect to z, I, j, k. Start taking the determinant, and right off the bat, the very first component that I would compute is the y partial of that minus the z partial of that. So what's the y partial of yz? Well, let's see. What's the z partial of x squared z? Well, x squared. So that the first component is going to be, the first component of the curl is z minus x squared. Not 0, done. No anti-gradient. Walk away. You can glance at this vector field, in other words, and realize that it does not have an anti-gradient, so don't waste your time thinking about the fundamental theorem line integrals. Everybody see how that works? It's pretty cool. Okay. All right. So here I computed the whole thing. I computed all 3 of the components, but you can tell that it's non-zero simply after looking at the first component in this case. Now, bad news, if the first component were 0, then you do have to look at the second and third. In order to conclude that it is 0, you have to compute all 3. But the not 0 sometimes is a freebie. So what about this next one? Let's look at this vector field, and we're computing a flux of it, and I claim it leaps off the page pretty well. Since there's no x's in there, there's no y's in there, and there's no z's in there, divergence is clearly 0, and that tells us information. Now it tells us that there is an anti-curl. I don't know how to find the anti-curl, but okay. Still, I know that there is one. And furthermore, it tells me that this vector field is surface independent. Right? So I've got options. And again, it comes from a glancing sort of look at our vector field. Okay. Two-dimensional example. This one's a little bit more work. Got these 2 components here. And to compute Green's, if we're going to try to use the fundamental theorem of line integrals, now again, we've got a parameterized curve. I could chapter 5 this problem. I don't really want to. Golly, look how ugly that is. The vector field with the, oh my gosh. So can I use the fundamental theorem of line integrals? Well, compute Green's operator. Right? Again, we're in R2. Got a vector field, interested in a line integral. Compute Green's operator. If I were to get 0, then there's an anti-gradient. Lifetime argument. And so there's more work to do here to make it work out, but in fact, yes, the Green's operator is 0. And so then I can proceed looking for the anti-gradient, knowing that it's not knowing that it exists. Yeah. Okay. All right. A couple of physics things I want to talk about very quickly. But these lifetime theorems give rise to certain physics concepts that otherwise we couldn't talk about. So in particular, now you all know about electric fields, right? You have a charged particle that makes an electric field. One of our theorems, one of our facts about physics that we talked about is that the curl of the electric field was the negative time rate of change of the magnetic field. So in particular, in a steady state where the electric and magnetic fields are constant, so in other words, if there's not some sort of fluctuations going on, if you have a steady state situation, then the magnetic field is not changing, which means that the curl of the electric field is 0. And the fact that the curl of the electric field is 0 means a lot of things. It means, for example, this electric field is path independent. From a physics point of view, you could say that, well, if it's path independent, then that means that we can talk about the amount of work that it takes to move through the field from a starting point to an ending point. Doesn't matter which path you pick. There's a well-defined notion of work there. So you can talk about potential energy. Said differently, you can find an anti-gradient. And that anti-gradient is called the potential function. So this is the electric potential function. There's a minus sign there. That's this is just a physics thing. It's a relic of the fact that gradients point uphill, but electric fields point away from the electric potential. So the gradient vector of the potential would point toward it's an awkward little minus sign issue. It's a physics thing, and I don't want to worry about it in this class. But the point is, you have this function that represents electric potential energy, and they call it V. The units for electric potential, and something I'm sure you all have heard, it's voltage. Right? So volts is that unit. So different points of view that you might have seen in the past for volts, and what is electric potential. Pretty good way to think about it is that voltage is the anti-gradient of the electric field. Right? So if you have a circuit, you can talk about the volts at various different points along the path, thinking about high potential, low potential, and as you move through resistance, you get voltage drops, etc. It's a common way to think about it. But that's if you're confined to a circuit. If you have, in some sense, a kind of a one-dimensional little problem. If you have a three-dimensional problem where you have an electric vector field and there's no wires anywhere, now what's voltage? This is the way to think about it. It's the anti-gradient. It's the potential function. I like to call it the anti-gradient of the electric field. Okay. Said differently, it's the function whose gradient gives you the electric field. Okay. The next thing I want to show y'all, I didn't learn until I was taking junior level physics classes as a physics major, and way back when. But you can make this exact same observation about magnetic fields one notch over. And the reason one notch over is because this other of Maxwell's theorems says that if you have a magnetic field, its divergence is 0. That's just what Maxwell's theorem says. Right? The curl of the magnetic field is not 0. The divergence of the magnetic field is 0. No divergence being here on the diagram. That's 0. Again, we make a lifetime argument, and what it tells us is that the magnetic field is the curl of a different magnetic field. And analogously, in the same way that we call this the electric potential function, analogously, this gets called the magnetic potential field. Oh, I'm circling the wrong thing. So, what do you do with it? What's it good for? All right. Well, let's look back here. What is the potential function good for? Well, potential tells you about line integrals of this field. If you're interested in the line integral of the electric field, said differently, if you want to know how much work it takes to move along a path resisting an electric field, then, well, you look at the potential at the start and the potential at the end. It's the change in the potential energy. So a line integral relates to the difference of two values of that function. It's a fundamental theorem of line integrals, right? Analogously, magnetic potential field tells you something about magnetic fields by way of Stokes' theorem. So specifically, if you're interested in magnetic flux, the flux of that magnetic field through some surface, a line integral around the boundary of that surface of this magnetic potential field will compute that magnetic flux for you. So it's very analogous to the idea of electric potential and voltage. It's just that because of the way this fits in on the diagram, it's not a function, it's a vector field. But it's used in an analogous way. Okay. One last quick comment. I'll be very quick. I think it's kind of nice that boundaries have a similar fact, and we do have to worry about issues with tying knots and that kind of thing. And so there's a few exceptions out there, but a nice way to think about surfaces and etc. is that every domain either has a boundary or is a boundary. And so what I mean by that, let's look at a couple of examples. If you look at a sphere, it doesn't really have a boundary. Right? Where's the boundary of a sphere? There isn't. You can say the boundary is 0, but there kind of is no boundary, right? Well, that coincides with the fact that it is the boundary of this ball. On the other hand, here's a surface that has a boundary. This surface has a boundary. Well, in fact, let me draw the surface better here. Here's the surface. It has a boundary. Whoops. In the form of those 4 pieces of curve. And because it has a boundary, that's related to the fact that it is not the boundary of something else. Right? Now, again, this is not a perfect rule, but with the exception of some pretty weird counterexamples involving knots, this is pretty usually true. I think it's a pretty nice way of thinking about things. So if you want to know if something is the boundary of something, look and see if it has a boundary itself, and vice versa. Okay. All right. I guess that'll do it for today. And yeah, we will next time. We'll talk about. This is just a bunch of examples. I'm going to give you some more discussion about how to make effective use of the diagrams. But it's basically just a bunch of examples. So we're going to go pretty quickly through this and then go into optimization tomorrow. Okay. See you guys later.